Now we will solve the question number 14. A certain observable in quantum mechanics has a 3 cross 3 matrix representation as follows. This matrix. Now it is asked, find the normalized eigenvectors of this observable and the corresponding eigenvalues, and it is asked, is there any degeneracy, and second, give a physical example where all this is relevant. So as we know that if x is an eigenvector corresponding to operator a and eigenvalue is lambda x, that means a minus I lambda into x is equal to 0, which implies that the determinant of this matrix, unitary matrix, is equal to 0, which means here the matrix is 1 by root 2 0 1 0 1 0 1 0 1 0 minus lambda 0 0 0 lambda 0 0 0 lambda. Its determinant will be 0. That means minus lambda 1 by root 2 0 1 by root 2 minus lambda 1 by root 2 0 1 by root 2 minus lambda. Its determinant is 0. This implies minus lambda into lambda square minus half minus 1 by root 2 into minus 1 by root 2 lambda is equal to 0, which means minus lambda lambda square minus half minus plus lambda by 2 is equal to 0. Means lambda minus lambda square plus half is equal to 0. This means the value of lambda will be either 0 or lambda equal to lambda square is equal to 1, which implies lambda equal to plus 1 or lambda equal to minus 1. That means the 3 eigenvalue corresponding to the given operator is eigenvalues are lambda 1 is equal to plus 1, lambda 2 is equal to 0, lambda 3 is equal to minus 1. Now let us calculate the eigenvectors. Suppose that x is the eigenvector which is x1, x2, x3. That means Ax should be lambda x, which means 1 by root 2 0 1 0 1 0 1 0 1 0 into multiply x1, x2, x3 should be equal to lambda x1, lambda x2, lambda x3. This means 1 by root 2 x2, 1 by root 2 x1 plus x3, 1 by root 2 x2, this is equal to lambda x1, lambda x2, lambda x3. So this means that 1 by root 2 x2 is equal to lambda x1 and 1 by root 2 x1 plus x2 is equal to lambda x2 and 1 by root 2 x2 is equal to lambda x3. Now from these two equations we can see that lambda x1 is equal to lambda x3. That means lambda x1 minus x3 is equal to 0. That means if lambda not equal to 0, then x1 is equal to x3. That means for the two non-zero eigenvalues, that means for lambda equal to plus minus 1, these two are equal. Let us assume that these two values are 1. This is say suppose that. Now if x1 and equal to x2 equal to 3, then what is the value of x2? Let us calculate that. That means 1 by root 2 is equal to lambda x2. That means x2 is equal to root 2 by 1 root 2 by lambda. Sorry, root 2 by lambda. Now for lambda equal to plus 1, that means x2 will be plus root 2 and lambda equal to minus 1, that will be x2 will be minus root 2. Now let us calculate the eigenvalue for lambda equal to 0. For lambda equal to 0, we simultaneously get from this equation and this equation x2 will be 0, lambda equal to 0 means x2 equal to 0, and from this equation we will get x1 plus x3 is equal to 0, which means x1 is equal to minus x3 is equal to, suppose that is equal to 1. Now our three eigenvector corresponding to lambda equal to 0 is 0 means x equal to 1, that is minus 1, and x2 equal to 0. Corresponding to lambda equal to plus 1 is 1, 1 and root 2, and the other is lambda equal to minus 1 is 1, 1 minus root 2. Now let us normalize these three. If we normalize, that means 1 by 1 square plus minus 1 square, it's root 2, 1, 0 minus 1. This means 1 by root over of 1 plus 2 square, 2 plus 1, 1 root 2 1, which is nothing but 2. So similarly here we can get 1 by 2, 1 minus root 2 1. So this means 2. So these are the three eigenvectors corresponding to three eigenvalues. That means for each and every eigenvalue there is a distinct eigenvector. That means there is no degeneracy. There is no degeneracy. And this matrix, this operator actually corresponds to this, physically correspond to a system whose spin is 1. and that means its component will be +1, 0 or -1. As we know that for spin half system, the quantum the space quantization means the component of spin half object will be either plus or minus half. Similarly, the quantization rule for the spin 1 system will says that the component of the spin 1 system can only take +1, 0 or -1. So this operator actually correspond to spin 1 operator. Now let us solve the question 15, which is, now let us solve the question 15. In question 15 it is asked, let A and B observer suppose the simultaneous eigengates of A and B from a complete orthonormal set base case. Can we always conclude that AB is equal to 0? Let us prove that. If your answer is yes, prove this assertion. And if your answer is no, give a counter example. Let us see that. Suppose an arbitrary eigenvector alpha. Since these gates are complete orthonormal, that means this can be the basis of the gate vector space. That means alpha can be represented in terms of these gates. That means alpha can be written as summation of A dash comma B dash gate A dash comma B dash A dash comma B dash alpha. This is nothing but the identity operator, which is actually completeness of these gates. And we know that any orthonormal set of base gates can be represented as complete set, and that means we can write these things. So that means this is equal to A dash comma B dash. This is nothing but a number, complex number. Let us write that Cn C A dash comma B dash A dash comma B dash. Now let us operate this gate with the operator A comma B its commutation. It will give summation of A dash comma B dash C A prime B prime A comma B A B. Now let us calculate what is the value of these things. Now A comma B A B, which actually means AB minus BA operate on the gate A dash B dash. Since this is also simultaneous eigengates of the A and B operator, that means, as we have previously studied, that means if we operate this state with AB minus B A prime B prime, which actually means A B A prime B prime minus B A prime B prime. So since it's a simultaneous eigengate, that means if we operate with B, it will get the eigenvalue corresponding to this operator. That means it will get B dash A dash B dash and minus B A dash B dash. A dash is the eigenvalue corresponding to operator A and B dash is the eigenvalue corresponding to the operator B. That means B dash A dash minus A dash B dash yes B dash. That means since these two are the numbers, and we know that the number are it completely commutative. That means A is equal to 0, means A dash B dash equal to B dash A dash. So A dash or B dash. So that means for any eigengates, actually simultaneous eigengates a comma b, a prime b prime is equal to 0. That means this term will always give 0. That means a comma b comma alpha commutation of operator on alpha always gives 0 alpha. That means it is nothing but a null operator, which means a comma b is equal to 0. That means a comma b is commutative. So we have proved that these a comma b, a and b are the compatible operator. Now let us solve the question 16. Now solve the question number 16. Here it is asked two Hermitian operators anti-commute. That means a comma b is equal to 0. Now is it possible to have a simultaneous eigengates? Now let us check that. That means a comma b will operate on any state will give 0. That means if we operate on some simultaneous eigengates a prime b prime is equal to, then is also give 0. That means let us check that whether or not operating on a simultaneous eigengates this anti-commutation give us give us back 0 or not. So let us check that ab plus ba on a prime b prime, since it is a simultaneous eigengates, that means it will give a prime b prime plus b prime a prime on a prime comma b prime. That means 2 a prime b prime, and a prime b prime is not equal to 0 in general. If a prime not equal to 0 or b prime not equal to 0, this is not equal to 0. That means in general, if we operate on the simultaneous on a some simultaneous, if suppose it has a some simultaneous eigengates, then it should not give 0. That means this is not equal to 0, which means these two statements are not true. If these statements are true, then if these statements are true, then this statement cannot be true. That means a comma b, if a comma b equal to 0, if a comma b equal to 0, this does not means then this a comma b operator have a simultaneous eigengates. A no. So that is that. Now let us solve the question 17. In question 17, it is asked two observable A and B which do not involve time explicitly are known to commute A, B, yet we also know that A and B both commute with Hamiltonian. Prove that the energy eigenstate are in general degenerate. So let us prove that. It is a very important concept for the quantum mechanics. So let us prove that. Suppose n is an eigengates of the Hermitian operator corresponding to the eigenvalue En. That means Hn is equal to En. Now since A1H is 0, if we operate on some state, suppose that A1H on eigengates of the Hermes H Hamiltonian, it will give also 0. That means A1Hn minus A1n will give 0. That actually means A1n is equal to En A1n. This means this A1n, total A1n, is an eigencase of the Hamiltonian H. But if that means n also eigengates and this alpha A1n also eigengates of Hamiltonian, that means if H is not degenerate, then this alpha should proportional to n. That means alpha should proportional to A1 n, suppose that. That means A1 n, that means n should be also an eigengates of the A1. But we know that not only A1 is a compatible operator of Hamiltonian, but there is another operator A2 which is also compatible operator. That means we again know that means A2n for non-degeneracy, we need that A2n is equal to an to n. This n also an eigengates of the operator, but if the non-degeneracy of H holds, that means these two relation holds, this relation and this relation holds. Now let us check what is the commutation relation then will be A2 on some alpha, and since n is the eigengates of a Hamiltonian and Hamiltonian is Hermitian, then we can write summation of n alpha n if we operate on this sum state is actually alpha equal to that. So that means if we operate on this state, we'll get A1 A2 summation of n operate on n minus A2 A1 n alpha n. Since these all, we suppose that these all are non-degenerate, that means this equal to summation of n A1n A2n minus A2n A1n n alpha n. And since these two are in general constant numbers, that means these are commutative, that means this equal to 0. But as we know that A1 comma A2 is not equal to 0, that means our assumption that n is non-degenerate is not true. That means the eigengates corresponding to the Hamiltonian is degenerate. That means corresponding to one eigenvalue, there has multiple eigenvalues. vector corresponding to same eigenvalue. This can be vector or ket. In quantum mechanics, it is actually ket. Ket, multiple eigenkets corresponding to the same eigenvalue. As an example, we can say that suppose a Hamiltonian operator H equal to p square by 2m plus some velocity r, plus some potential which depend on r, and some operator a1 equal to lx and some another operator equal lx to ly. Since we know that a1 comma a2 lx comma ly is not equal to 0, that means this Hamiltonian is degenerate. That means there could be many eigenkets corresponding to same energy, which physically means that this state can have angular momentum corresponding to Lx, suppose 1, and corresponding to Ly is 0, but the total energy is remain same. So this is a state, and again suppose that corresponding the angular momentum of corresponding state is Lx is 0 and Ly is 1, and again the total energy is same. So that means these two states have same energy, but their angular momentum are different. That means these two states are degenerate state corresponding to the same energy En. So that is an example of that problem. So thank you.